Hi there, my name is Kim Kaloran, and I'll be your host for today's event. First, I wanted to thank you all for joining us for today's webinar titled The Speed Myth, Perceptions versus Reality. Before we get into today's topic, I wanted to give you a little overview of who Stratasys is. For those of you who aren't familiar with our company, Stratasys makes 3D printers and production systems based on patented fused deposition modeling, or FTM, technology that can produce prototypes and production parts directly from 3D CAD data using engineering-grade thermoplastics. We also operate Red-Eye On Demand, which is an online rapid prototyping and digital manufacturing service. And as you may have recently heard, Stratasys has merged with Objet, which is an Israeli-based manufacturer of 3D printers that use inkjet-based polyjet processes to create a 3D model. So, for today's event, I'd like to welcome our speaker, Mr. Todd Grimm. Mr. Grimm is a consultant in the 3D printing industry. He's an editor, author, public speaker, and industry advisor with 22 years of experience in the world of 3D printing. He's recently been named as one of TCT's 20 most influential in the industry. Now, without further ado, Todd, you've got the floor.
Well, thank you very much, Kim. It's my pleasure to be here today to talk about what we've titled the speed myth. And this is actually something that I'm pretty passionate about because, as indicated here in my very first bullet point, time is not a constant. It's inappropriate to look at 3D printing technology and say that one is always the fastest or one is always the slowest, because there are so many aspects with respect to time that affect the equation. And that'll even change right from at the highest level based on your type of parts and your geometry, your needs, your wants, and your desires. So the key thing to walk away with here in our subtitle of the presentation is perception versus reality. Since you can't make the generalization that one technology is fast or another is slow or something in between, if you were to look at a video or stand before a 3D printer and watch the operation and walk away saying that that is a fast technology or that's a slow technology, that perception could very well be totally inaccurate. It might lead you to the wrong conclusion, and therefore, if you're in the buying mode, it could lead you to the wrong buying decision. And the reason for that is speed is a relative concept in the world of 3D printing, as it is in many other aspects of our lives, but it depends, as I've already said, on what your process is, what your needs are, what parts you're going to be building, and what your goals are. And along the way, that's one set of variables. The other set of variables are buried within the 3D printing technologies. So since there's so many variables, there's so many different conditions on how you may want to operate your machine or the kind of parts you want to build, you can't make the global statement that one is faster than the other, and hence the speed myth. And to drive this point home, I have two images here. One's of a steam locomotive, the other one of, of a bullet train. Now, in terms of raw speed, we can emphatically state that the steam locomotive is going to be slower than that bullet train. But as a passenger, do you really care about the speed, or is it more important how fast you get to your destination? And I'm pretty sure it's going to be the latter. And if it's the speed to your destination, we can't decide which of these two trains are fastest because we don't have all the variables. We don't know if they're riding the same rails and therefore have the same amount of mileage between them. We don't know how many stops are between the origination point and the destination. We don't know how long we stop at each point. 3D printing is much like that. We've got to identify all the variables. And so I think your goal is going to be arriving at the destination, which is delivery of a usable 3D printed part in the fastest way. But I'd also like to put on another layer, which is efficiency, which incorporates speed, but also how much effort goes into the process, how much opportunity is there for delays and bottlenecks, how simple does things move along, and how smoothly do they move along. So the speed myth in this presentation really relates to this concept I think that you're driving to and is important to you, which is an efficient process which encompasses speed of delivery. Now, what we're going to do today is cover 5 areas, and I'm not going to talk about individual technologies and point things out because, as I've said, perceptions can be misleading and there are no generalizations, so it wouldn't be fair of me to offer those up. Instead, what I'm looking to do today is to talk about these 5 areas to give you some indication of the things that you may want to investigate in an evaluation of 3D printers if speed is an important parameter in your decision-making process. Now, those 5 are the time for the total process, not just build time. We'll then move into time, and I've got hands-on here indicating that we're talking about automated time versus manual operation. The third topic is going to be time variables, those things that affect time through the 3D printing process. Finally, time's effect on speed, because what you may not know is that your system may slow down over time and thereby affect the speed of delivery. And finally, time buckets, and this is something that relates to your standard mode of operation, and it can actually throttle the fastest system and accelerate slower systems, making them equal. And we'll get into details in each one of those. And to start off with time for the process, the fable of the tortoise and hare popped to my mind immediately as I started putting this webinar together. Of course, we all know this fable. The tortoise plods along, heads straight for the finish line, wins the race because the hare darts along in one leg, stops and dawdles around and just kills time, then races again, and then stops and dawdles around a little bit, and then races again, but doesn't cross the finish line first. In 3D printing, those legs of the race that the hare's creating, the start and stops, are actually part of the total process. It's not just build time. What you need to evaluate is more than build time. You've got to evaluate the total process time for what I've indicated here is file, which is file preparation, prep, which is machine preparation, the build time, which is important, but it's just one element, waiting time, that's after the machine finishes, but before you get to the final process, which is post-processing. You've got to evaluate each one of those 5. And a little arbitrary diagram here, 2 timelines. The one is the gray one, the other is the yellow one. You can see that highlighted with a red outline is build for both of them. The gray one, the build time is shorter. The gold one, the yellow one, the build time's longer. But if you look to the right, you can see that the yellow crosses the finish line first. It becomes the winner of the race, even though in the build time it would look like the tortoise. Now, give you some information on each of those 5 steps, information that will allow you to ask intelligent questions and to dig in to what will affect your total throughput and your delivery time for your prototype parts and additively manufactured parts. First step, and again, this isn't specific to any one technology, and these are just some of the highlights. I can't get into all the details because the technologies are so different and have so many different variables and factors. But overall, these will be true of most systems. Right up front, you've got the time to prep your file. This is once you've received the STL file, how much time goes into processing it to make it buildable. And that'll include orienting the part. That'll include the time to add support structures to the part, the time to slice the part, and the time to apply the build parameters, which may be default build parameters, which is a simple one-click operation for some systems, or you may actually be using some custom parameters, which may take more time. So it's important to investigate each one of these aspects in file preparation to come up with your total tally for your parts on how long they'll take. And one thing I don't have listed here is there may be the need to do some file repair. STL files are notorious for having small gaps and overlaps and inverted normals that make them unbuildable files. Well, some technologies are more sensitive to small deviations and errors than others. So you may even find in file prep that one system you need to do STL repair, another system you don't. The STL repair may require a third-party program, an additional step, which all adds time. Now, an area that very few people talk about and really doesn't come to mind until you actually own the system is machine prep. Once you've got the file downloaded to your 3D printer, before it actually starts printing that first layer of geometry, you've got to ask the question, what goes into the process? What goes into time? Because there will be time, possibly for routine maintenance before every build. You might have to clean some rails, purge some heads, do routine operations like that. But more importantly, you want to understand how much time it takes to load material. That could be replenishing material in between builds, or it can be swapping material. If you're running material A for the first job and you want to run material B for the second job, that can take 15, 20 minutes. It might take upwards of a couple of hours, depending on the technology. You can see that couple of hours can really add some time. And another area in the machine prep that really goes unnoticed is warm-up. A lot of these processes have a thermal component to them. They may be thermal processes or require materials to be brought up to a certain temperature. And that can take as little as 5 or 10 minutes from an idle state up to or upwards of several hours. So it's important to understand what goes into machine prep before that machine starts building to decide how fast a process is. Then we go into build, which I'm going to get into the variables there later, so I'll talk about that in just a few seconds or a few minutes. The next step, also often not thought about, is what happens after the machine stops building the part, but before you can actually touch that part and move into post-processing. There is a lot of opportunity for delays or lost time in waiting. You may have to allow the part to sit in the machine to drain excess material from it. You may have to allow the part to rest in the machine to fully harden the materials. But the biggest time component may be back to the thermal processes, a cool-down period. You may have to allow the machine to cool down for minutes or maybe as much as hours before you can even touch the part. In one case, with one class of technology, the general rule of thumb is you double the build time. For every hour of build time, you actually have to spend another hour in cool down. So you can see that that can really add up. Finally, we get into post-processing. So now you can handle your parts, and you're going to go into operations that may include cleaning the parts to remove residual materials. You might have to go through a secondary curing operation to fully harden the parts, or maybe a thermal post-cure if you're looking for higher-end mechanical or thermal properties. That would be done in a regular oven. You remove the material, and then you also remove support structures. And then finally get to the point of sanding the part and finishing and painting to your needs. It's important to understand all those steps and the time that will go into the process for your typical parts. Now, that's the total process and what goes into it. Another aspect of time and speed of delivery is manual versus automated. Now, this is one that may or may not be important to each of you as individuals, but something to consider. I personally think that a 2-hour process that's entirely manual versus a 2-hour process that's entirely automated are two different things. I'd view the fully automated process as being more efficient in delivering the parts because we're looking at resource demands. So if there's manual processes where someone has to be there, hands on the part, doing the operation versus hitting a button and walking away, you're looking at having the resources available for that duration of time to complete the operation. And those resources may or may not be available, which leads to the second bullet point, resource availability, which actually adds maybe a 6th or 7th step. If you look at the timeline here, over to the far right, the second in from the right, is staffing. You might have an operation that's manual that affects your efficiency or the efficiency of the throughput because you're sitting and waiting for someone to come around and staff that operation, to execute that operation. Hence the picture of the log jam I have here. A friend of mine in the toy industry spoke to several years ago actually gave up on using a technology that produced very nice parts for small figurines that they were doing. They loved the technology, loved everything about it, but they stopped using it because they could produce dozens in a couple of hours, but it would take them 2 or 3 days to get the manual labor, the man time, the resources, the human resources into the post-processing operation to even start touching the parts. So a couple of hour turnaround time turned into 2 or 3 days for them. So I think automation is something really critical to consider in your evaluation of speed, and most importantly, as we move more and more to the personal class 3D printer, that kind of machine that's sitting right next to you in your office, and it's self-serve. So you become not only the consumer of the prototypes and parts, you become the maker of them. Now I really think automation comes into big play because while you're busy doing a post-processing operation or manually doing something in the 3D printing operation, you're not doing the job that you're paid to do. So there's forest fires raging, there's projects to be tackled, tasks to be done, and your decision is, do I tackle those or do I go and do the manual operation? The next area I want to talk about is build time, or actually the variables that go into defining the total build time. Build time is not a constant because it depends on the parts that you're building. We have 2 different modes of operation for building for most of the technology. You can have presets, which are default build styles. Simply select from a drop-down list and say apply style A, and that's how the part will be built. Or you can apply your own custom configurations, custom styles to get different qualities for your part. Well, even with the presets, the fixed build styles, you'll find that there's a lot of variance in build time based on things as simple as orientation of the part, the volume of the part, the surface area, and the footprint. Matter of fact, if you took two identical parts in 3 of these 4 categories and left only the 4th category as a variable, you change that one up, you will have 2 different build times in most of the technologies. Now, let me explain these real quick. Orientation is the orientation of the part. I think as many people recognize, the taller a part is in 3D printing, the longer its build is going to be. So orientation has a big effect on build time. The volume of the part, that's the total cubic inches of material that go into your part, will also, well, I shouldn't say will also, may also have an effect on time for some technologies. Surface area, now this is one that people really don't think about. There can be different build approaches or styles. The system may perform differently on external and internal skins than it does on all the area that fills in between. And usually what's being done is things are changed to improve surface finish or feature detail. Well, to change surface finish and feature detail often means that the process is slowed down. So if you have more surface area, more exposed area on the part, you might have a slower build time or a longer build time. And finally, footprint. Let me offer the example, create a mental image of a box, simple rectangular shape of 1 inch by 4 inches by 6 inches. Let's say we build that part in 2 different orientations, both of them with the 1 inch being the build height, the Z height. All we're going to change is the 4 by 6 footprint. That's the area on the build platen. If you were to, in some technologies, if you were to build with the 4 inch being the Z-axis or the X-axis, that'd be left to right, versus the 4 inches being in the Y-axis or front to back, you can have 2 very different build times. So you can see right there we have variables that are related to your parts and your applications that drive build time, meaning that you cannot treat time as a constant, and generalizations are not appropriate. Now, when we get into options, that's the default presets, the default build styles. Now you'll also have some options available to you in most of the technologies, or all, and these can affect time, also affect time. So in the build style itself, of those default styles, you may have options for the layer thickness, how thin the layers are, the resolution of the part, so how fine does a laser track along the part, or what's its beam diameter, and other elements that affect resolution. You might also have the opportunity to change the fill style and the hatching, what goes on inside of the part. Got 2 examples shown here, and these are actually courtesy of our webinar host, Stratasys. They have a build style option called sparse fill that's shown here, which does solid exterior and interior walls that encase an internal honeycomb or scaffold-like structure to drive out a lot of material. Well, driving out a lot of material also drives out a lot of build time. So again, you've got to identify the build styles that you want from your possible vendors and understand what the time is for your parts. Another area of consideration is batching. And this will surprise quite a few people. Actually, in a recent benchmark, which I'll show you a chart from that, I was totally shocked at the effects of batching. And what I mean by batching is you can, in the world of 3D printing, consider 2 modes of operation as 2 extremes. One would be build each individual part as you need them. So build part A alone, and then part B and part C, and then part D and part E and F after that. Or you could take parts A through E, or F, A through F, and consolidate them into a single build. Now, this will be your mode of operation, and you'd want to look at your typical mode of operation to understand the effects on time. Will you build a lot of parts individually, or will you wait till the end of the day, amass as many parts as you can, put them in the machine, and let it run overnight? And the reason I bring that up, I'll pull data up from this was early 2011 benchmark that I had of 6 systems. And now you'll notice that there are no system names on here. Since this is a presentation based on the fact that you can't make generalizations without details and pinning down the variables, it would be inappropriate for me just to throw out the system names here. And that's not the point. What I really want to illustrate is the difference between consolidated and individual builds. Now, if you're really interested in which systems are which, there's a benchmark available at my website, tagrim.com. You can download that, get all the information. But when you do, I suggest you look at the type of parts that were done and all the operations that went into each one of the systems tested before you decide what's fast and what's slow. But back to the key point here. The blue columns are consolidated builds. I had 4 parts in the benchmark. And what consolidated builds means is I built those 4 parts in as few runs of the machines as possible. In some cases, all 4 in a single run. Other cases, maybe 2 of the 4. The yellow bars behind it are the same parts built individually. So each of the 4 parts had a separate run of the 3D printer. Now, these are total process times. This isn't just build time. This is from opening the STL file out to final post-processing. I want to draw your attention to the second from the left set of columns. So that's the blue and the very tall yellow behind it are one system. And I guarantee you that this is a system, if you stood before it and watched it print your part, you would swear that it's one of the fastest systems out there. Well, if you're building parts individually, you can see that it's the slowest system. It only gains its speed and becomes the 3rd fastest when you build in a consolidated fashion. And to the other extreme, if you like to bounce back and forth between single part builds and consolidated builds, you look at the system 3rd from the right that only has 8-hour difference, 8 hours of difference between consolidated and individual builds. So you may opt to go with a technology that's a little more stable when you bounce back and forth between your style of building parts. And lastly, orientation as its effect on build time. I already covered it lightly when we first started talking about build time, but here I want to make the point that orientation may not be entirely in your control. So if you see a claim of, let's say, a half a vertical inch per hour as a flat fixed time, and you take a cigar box, a 5-sided box, 1 inch by 4 inch by 6 inches, so 1/8 inch base plate, 4 walls rising up 1/8 inch thick, each one of those. If you took that box and said 1 inch tall will be my Z, the minimum Z, half an inch per hour, boy, that's only a 2-hour build. Well, because of constraints, you may not be able to build that part in that orientation on that machine, that technology. 2 reasons. One is quality of the part. Easiest example here is to consider a tube, a 1 inch diameter tube. Let's say it's 6 inches long. Well, in the world of 3D printing, for circular geometry, if you want it to be true, if you want the OD and the ID, the diameters of the part to be nice and circular, you're going to want those facing, or the profile of those facing the laser, the extrusion head, or the print head. Well, to do that means you're going to stand the 6 inch part straight up, and what you think is 1 inch or 2 hours at a half a vertical inch per hour becomes 6 inches or 12 hours of build time. It's beyond your control based on the quality of the part. More importantly, there are quality issues that may need to be addressed with a part that are based on, I hate to say the word deficiencies, but I'm going to go ahead and do that, deficiencies in the technology. A lot of the 3D printing technologies put the materials through a state change. You might go from solid to semi-molten to solid, or go from liquid to solid. And as they do, that can impart a lot of stresses into the part. And those stresses, if they're not properly countered by the technology, will cause a part to deform. So back to that 1 inch by 4 inch by 6 inch box, 5-sided box, as you start to, if you're to build it with a 1 inch Z, as you start to build that base plate, the 4 by 6 by 1/8 inch plate, you may have so much stress build up because you're curing or solidifying so much material in a single layer that it potato chips. It warps, it bows, it curls. And the only way to overcome that is to tilt the part upward, increasing the Z height, which increases build time. In one extreme case, on that same benchmark that I just showed you a table from, there's a technology that needed to have the part tilted up, but the layer thickness was so thick that when they tilted it, it looked heavily shingled. It looked like a really bad finish because it was just so heavily stair-stepped. And the only option they had was to take and it was a 1 inch by 4 inch by 6 inch part. The only option they had was to stand that part up on end, so the 4 inches became the Z, which therefore more than quadrupled the build time. So that's not all the variables in build time, but those are some of the things that you want to consider in your evaluation to discover what's truly the fastest. Now I'm going to move on to the fourth area, which is time's effect on time. And it's not a very good title for the slide. I know what I'm trying to say. It doesn't come across here, so let me explain. Over time, some 3D printing technologies will get slower. So if you were to build Part A on day one and it takes 4 hours, a year from now, you may find that that Part A builds in 5 hours, 6 hours, 7 hours, some additional time. And the reason for it are the possibility for it is twofold. One is if the system has an energy source converting the material from one into a solid form, and that energy source slowly degrades over time, well, it's going to take more time to process the part. Also investigate if there's any changes in the material's reaction to the processing. If you have a technology that you replenish material after every build by adding fresh material to something that's already been in the machine, the older material, the material that's already been processed, may have gone through some changes that affect its ability to cure, to solidify, to be processed as quickly as when it was fresh. So something to consider when you're looking at time or total speed and delivery time of your prototypes when you're evaluating the technology. Now I'm going to move on to the last topic, the last of the 5 areas that I want to bring up with respect to the speed myth, and this is time buckets. Now this is fully in your control. This is about how you will operate your 3D printers in an everyday fashion, a normal fashion. Now, I'll admit, it's always comforting to know that your 3D printer could respond at a moment's notice to emergency. So there's a design review meeting called, surprise, surprise, at 8 o'clock tomorrow morning, you need to rush out parts, or a big problem happens and you need to come out with a new redesign real quickly. Well, it's nice to know you can respond to that quickly. But I find from day to day, and this is talking with lots of customers, lots of users of 3D printers, that we tend to fall into standard operating modes. You know, I've already talked about parts individual or consolidated, and this is kind of back to that, but you'll fall into the operating mode of building parts as you need them or consolidating multiple parts in a build. And if it's the latter, if that ends up being your operating style, then you'll probably find yourself working in time buckets. Mentally, your schedule will operate on maybe a 4-hour cycle or an 8-hour cycle or a 24-hour cycle. And what I mean by that is you start to go into your days, your weeks, and your months with respect to your 3D printer, considering that you'll kick off a build at 8 in the morning and then one around noon if you have 4-hour cycles, then one around 4 o'clock. If you're an 8-hour cycle kind of company, it would be one at 8 and one at 4. And if you're 24 hours, it would be one at 8 in the morning and the next one at 8 in the morning. And I bring this up because this will actually throttle a fast technology and give some advantage to it, or bring a slower technology up to and possibly equaling something that's faster up to the point of post-processing. So what you're going to want to do is get an idea, if you can, of your operating environment, your typical parts, and then look at systems that can deliver in a 4-hour, 8-hour, or 24-hour cycle. But the most important point, a little image here indicating your 9 to 5 workday, which if you're like me, it's far from 9 to 5 anymore. But an example here, arbitrary example back to my grayish blue and yellowish gold lines. We've got 2 processes, and this is the total time up to removal of the part from the machine. And if we look at this, compare them without any other information, we say that the blue line is faster, higher speed than the yellow line. But let me throw a little calendar for the day behind that. What if you kicked off both builds at 8 o'clock in the morning? And what if you only operate on a single shift, meaning that after 5 o'clock, there's absolutely no one in the facility to take a part out, kick off another job, and start post-processing it? If that were true, with these 2 builds here, even though one is 3 hours longer than the other, effectively the speed is exactly the same. Both of the technologies would have parts ready for post-processing when you walk in the door the next day at 8 o'clock in the morning. Matter of fact, that yellow bar could go all the way out to a 23 3/4 hour build and still be the same amount of net time or throughput for the machine as the much faster build that runs from 8 to 5:30. Important considerations along the line in looking at speed. And I'm going to wrap up now. We've covered the 5 areas, that being total process time being more critical than build time, automation versus manual operations, how important it is in your decision making. Then we looked at the variables for build time. We looked at the effective time on your machine and your materials affecting the throughput. And finally, your time buckets. And with that, I really hope that you can see that there's way too many variables in 3D printing to make any generalizations about what's a fast machine, what's a slow machine, and what falls in between. And remember that everything is relative. Speed is relative. Key point here is that no matter what technologies you're looking at, always keep in mind that there's a relative component of speed to all the conventional and traditional methods. We're always going to be faster with a 3D printer if there's no tooling that exists or tool paths or setups or jigs or fixtures sitting there ready and waiting to machine or mold a part. We are going to be faster, so it becomes degrees, relative degrees of speed as you jump into 3D printing. And the key thing here is to know what's important to you in your evaluation of 3D printers, what your parts look like, what your process looks like, what your applications are going to be, what the needs and requirements of those applications are, so you can communicate those to those companies that want to provide you a system, and then you can inquire, what will the total speed be for my parts in these considerations? And I've got the image here of the Formula One car and the looks like a circa 1960 little commuter vehicle. This is back to the train analogy I had on my first slide. If I ask you the question now, which one of these two is fastest, I really hope that you say, I don't know. And you can't know because you don't know the conditions. What if they're both in commuter traffic? That Formula One car and that little commuter car from the 60s, both of them are going to get from point A to point B in exactly the same amount of time. And Kim, the last comment I want to make is this quote here. I've always loved this quote. Tried to find the source, but I found like 4 or 5 different people attributed to it, so I just went without a source on it, a citation. You can read it yourself, but I'm going to repeat it. There never seems to be enough time to do it right the first time, but there's always enough time to go back and do it again. Related to 3D printing, here, the use of this quote, I want to remind you that if you have a lightning-fast system that has all the speed you're looking for, but it doesn't produce a part to the quality needs that you have that meet your demands for your applications, speed is irrelevant because you're going to have to go back and do it all again. So make sure, my point here being, Kim, is make sure that you're balancing speed with all the other parameters for what you deem to be a quality 3D printed part. Kim, with that, that's what I've got. So I'm going to turn everything back to you.
Thank you so much, Todd. That certainly gives us a lot to think about as we're, looking at 3D printing technology. All right. So in a minute, we're going to start taking any questions that you may have. If you think of a question in the meantime, be sure to submit it through the Q&A panel. After the event today, you'll be able to find the recording of this webinar, along with some other downloads like the slides, the white paper that is around the speed myth idea as well, and also a calculation worksheet that Todd has been so gracious to help us with at www.stratasys.com/speedmyth. And also, as Todd mentioned earlier, there is a benchmark study available at tagrim with 2 M's.com. All right, now I'll take a look and see if there's any questions that are coming in. Looks like there's a couple here to start with, so please remember to use the Q&A panel if you have more. Todd, here is the first question from John. He's asking, can you give me an idea of the total process time for FTM?
You set me up as a straight man, John. Actually, I can give you some indication here because I've been trained on the Fortis systems from Stratasys, so I've run them and run through all the operations. And you're actually playing straight man, I think, for Stratasys because a lot of the advantages with delivery of parts, the total throughput, and the speed of getting your parts fall around the build time. In my experience, using the default build styles, what Stratasys calls a green flag condition, you can have a single file. Well, let's look at just one part in our mind right now for this answer. You can take a single part and you can have that prepped in 2 to 5 minutes really easily without working too hard. and almost across the board any part that you're presented with of reasonable size. Once you get the part prepped on the machine, my experience is you've got the file downloaded to the machine to do, there is no system maintenance required before firing the machine up. Let's assume that you do have enough material because it's on a continuous spool, so that's not something you have to take care of. Then it leaves us with the only component being warm-up, which, Kim, if I'm not mistaken, that was about 15 minutes if the machine was in an idle state, and maybe 30 minutes if it was from a cold start, a machine that had been shut down, turned off for a day or half a day or more. Build time, I'm not going to get in that. As I indicated earlier, so many variables. There's no way that I can quantify that. But if you're really interested, one of Stratasys's 3D printers, the dimension is in that benchmark, so you can take a look at that and see head-to-head what its build time was and total process time. For post-build, no delay at all. As soon as the machine ended, opened the door, yanked the parts out, got into post-processing, and then when I was in training, all of it was using the soluble support material, Kim, so that was an entirely automated process, and for the most part, I was taking the parts out, spent about 2 minutes ripping off the supports I could easily get access to, dropping them in the tank, and coming back about 2, maybe 3 hours later, and had parts ready to go. So, sorry, really elaborate answer there. Sorry about that, Kim, but give people some better idea of the FTM process.
Yep, that sounds about right. Good. All right, here's another one from Monica. She's asking, can you go back to the graph and tell me which bars are for which systems? So I will...
No, you don't. You don't need to go back, Kim. I know what you're thinking of doing. Monica's trying to see if she can weasel the answers out of me. Monica, no, I don't want to do that. Again, go to the benchmark. And everyone listening, I'm not trying to drive you to my website and trying to get you to go look at the benchmark, which is free, by the way. Please feel free to download it, but that's not my goal. It's just that it's very inappropriate for me to be throwing system names out there based on no other data, no explanation of when in the process, and you don't even know what the parts look like. So it becomes meaningless to identify which systems are which. Just focus on what that slide was all about, which is big differences for some systems between individual builds and consolidated builds.
Okay, sounds good. Here's one from Heather. She's saying, you lost me on orientation. Can you clarify why a part may need to be built upright?
Okay. Sorry, Heather, I lost you. It can get a little confusing, and hopefully I can clarify. I'll do my best. Okay, so imagine now, take away that 5-sided box I was talking about before. Just imagine a thin sheet. Your entire part is maybe a 4-inch by 6-inch sheet of material by 1/8 inch thick. As the material is being solidified or cured or deposited, the material is going to shrink a little bit. It's going to change in size, and as it does, and it's bonded to the layer before it and bonding to the material to the side of it, it's going to pull in. And as it does, it's going to create a stress that causes the part to lift on its edges. That's the most common situation, is lifting on the edges. Well, that's building the part flat. So what you'll do is tilt the part up, and now instead of having each slice being 4 by 6-inch sheet of material, if you tilt the part up just a little bit, each slice becomes 4 inches long by maybe an 1/8 inch thick. Oh boy, that's going to be hard to envision. So mentally take a sheet of paper and tilt it upwards at 5 degrees, and then take horizontal slices through it. That profile of the sheet of paper is all you'll be curing. You're minimizing the amount of material cured in one layer, and that reduces the stress, and then overcomes the challenge. The other one was related to the diameter. That could be related to anything circular, anything round, anything angled in an orientation. You may want to change that so that you get the best definition of the feature and or minimize stair-stepping. And what I didn't mention, Kim, hopefully Heather curious to hear about this, you may also have to change your orientation due to support structures. If a part's oriented in one way, the support structures may touch sensitive features that could be damaged when they're removed. And if you don't want that, you've got to change the orientation. Or you may also have to change the orientation because supports become embedded in inaccessible areas, something you can't get at to remove it. And if it's stuck in there, your part's basically useless because the support's right along with it. So you may have to change the orientation so that feature isn't supported. Think it's got it, Kim? That's the best I can do off the cuff.
Yeah, I think that makes sense overall.
All right.
Okay, so here looks like we've got a couple more that have come in now. Rob asks, why does batching parts improve speed?
Okay, that's a good question, Rob. For every process, for every 3D printing process, in between layers, there's going to be some operational overhead, some non-value added time, where the clock is ticking away, but the part isn't being grown or built. And that operational overhead can be for things like spreading a fresh layer of material. It can be for sensing the power of a laser. It can be to make sure that the home position is held true so that the part's accurately drawn. So it can be a sensing and diagnostics operation also. Well, that happens in between each and every layer, but it only happens once. With every build, you'll only need to do that once. Let me give you a specific example, if I may, Kim, with FTM. On a layer, when you go from building the model to building support structure, the heads actually go off, do a quick purge, but the one that was idle has to be brought up to temperature, and that's probably about a 15 to 20 second operation. So that 15 to 20 seconds is lost on each and every layer. Well, if you add more parts in, you're not doubling that lost time. You're actually amortizing it or spreading it across all parts. So that's how a consolidated build can be faster than sequentially building parts individually.
Very good, thank you. I think we got time for one last question here. Amir is asking, what's the best way to get an understanding of everything that affects time for a technology?
Ask questions. Really, my number one recommendation, or actually two top recommendations, is benchmark your typical parts. And vendors aren't going to like it. Stratasys is probably going to cut me off right now because benchmarking doesn't mean one part. Try to get a reasonable, you don't want to put anybody through too much work, but try to get a very reasonable number of samples of your typical type of parts. Ask them to be built. Have the vendors document all the time that went into it. And if you have two sample benchmark parts that are different enough, some kind of characteristics, you'll start to get some sense as to what affected time. The other thing to do, and that's true of not only for time, but that's true for all quality parameters, considering operational overhead, what goes into the process, everything. Benchmark, ask questions. And my other recommendation is to turn around and ask those very same questions of users. So reach out to somebody using the technology and say, hey, here's what I'm trying to do. Here's my understanding of what affects speed. What don't I know? And let them give you insight and the benefit of all their experience.
Great. Makes a lot of sense. Well, looks like our time is up. Thanks again, Todd, very much
for your
help. Yeah, good. If we didn't get to your question live on the call, we'll be sure to follow up with you after the event via email. We'd like to thank each one of you for your attention during this presentation, and now I'm going to turn it over to our operator who will close out the event. Thank you.